All right. In this calculation, we are required to find the molecular formula of a compound, and we're given that 2.00 gram of the sample of the compound gave 4.86 gram of carbon 4 oxide and 2.03 gram of water on combustion in oxygen, burning in oxygen. The compound is known to contain 3 elements: carbon, hydrogen, and oxygen. And we're also provided with the molar mass of the compound, 144. All right. The strategy in this work is to use the mass of carbon 4 oxide produced to calculate the mass of carbon present in the compound. Next, we use the 2.03 grams of water formed to calculate the mass of hydrogen present in the compound. And based on our knowledge of the mass of carbon and mass of hydrogen, we can find the mass of oxygen also present by taking advantage of the 2.0 gram total mass of the sample. So this will provide us the elemental composition of the compound: carbon, hydrogen, and oxygen. And from this, we can find the empirical formula. From the empirical formula, we proceed to the molecular formula. So the flow chart of solution is to establish the elemental composition. We establish the elemental composition of the compound. The elemental composition, this means the amount of individual elements contained. Elemental composition. From the elemental composition, we progress and obtain the empirical formula. The empirical formula. The empirical formula. And once we know the empirical formula, we can make use of the molar mass to obtain the molecular formula. We make use of the molecular formula. We obtain the molecular formula using the molar mass provided. So this is the flow chart. We have 3 stages for this work: determination of the elemental composition by stoichiometric calculation, determination of the empirical formula by our tabular format, and then the determination of the molecular formula by taking advantage of the molar mass provided. So let us get straight off into the solution. I have to take this away. Straight off into the solution. So we have 4.86 gram of carbon 4 oxide produced. The question then becomes, what mass of carbon is present in 4.86 gram of carbon 4 oxide? First, we need to establish the molar mass of carbon 4 oxide. Let's go. Molar mass of CO2. Of course, relative atomic mass of carbon given to us as 12, plus that of oxygen, 16, multiplied by 2 because oxygen atom occurs twice. And by evaluating this, we have 16 multiplied by 2 gives us 32, and 32 plus 12 gives us 44, the molar mass of carbon, 44 grams per mole, which means 1 mole of carbon 4 oxide has a mass of 44 grams, the molar mass of carbon 4 oxide. All right, now let us get into it. 4.86 gram, 4.86 gram of carbon 4 oxide contains what amount of carbon? Now we're using our dimensional analysis technique. So we have to multiply and cancel units. The denominator is the first place to go. We have a gram of carbon 4 oxide, so we can draw a relationship showing us mass of carbon 4 oxide related to mass of carbon, and the molar mass will help us do that. 44 grams of carbon 4 oxide contains 12 grams of CO2, or of carbon rather. So this mass of carbon, 12, contributes 12 grams. Carbon contributes 12 grams out of the 44 grams in the molar mass. So we say 44 grams of carbon 4 oxide. The molar mass contains 12 grams of carbon. And that is it. This evaluation of this by multiplying and dividing gives us the answer we desire. So we can see the units already take care of themselves. Gram of carbon 4 oxide eliminates gram of carbon 4 oxide. And we have the prevalent unit, gram of carbon. So by multiplying these, we obtain 1.33. 1.33 by using our calculator, gram of carbon present in the organic compound. In a similar manner, we want to establish the molar mass of water in a similar manner. So let us establish the molar mass of water, but I have to take the traces away. Now let us recognize this value, and we need this value for our continuation. Now the molar mass of water. Establish the molar mass of water. The same way you establish that of carbon 4 oxide. Molar mass of water by adding the relative atomic masses. Hydrogen occurs twice, and the relative atomic mass of hydrogen is given to us as 1 right there. So we have hydrogen 1 relative atomic mass multiplied by 2 the number of times the atoms of hydrogen occurs, plus that of oxygen, which is 16. And by evaluating this, we have 1 multiplied by 2 gives us 2, plus 16 gives us 18 gram per mole. Once again, we can see that out of this 18, the mass contributed by hydrogen is 2 right there. And this means 18 gram of water contains 2 gram of hydrogen. We're going to employ this relationship in our dimensional analysis. And now the question becomes, 2.03 gram of water contains what mass of hydrogen? So what mass of hydrogen is contained in 2.03 gram of water? That's the stoichiometric calculation. Let's go. So we start with 2.03 gram of water provided. And in our dimensional analysis, it requires cancellation of units on the left. The unit of the left should be targeted and cancelled. Gram of water. So let us draw the relationship that contains gram of water, and the molar mass gives us that relationship. 18 gram of water contains 2 grams of hydrogen. So we have that 18 gram of water, so that we can do that cancellation. 18 gram of water contains 2 gram of hydrogen. 2 gram of hydrogen. Beautiful. And now, as we can see, the units already cancel out. So by doing this multiplication and division, evaluating this result, we have our answer there, 0.23 gram of hydrogen. 0.23 gram of hydrogen present. That's right. Now we know the mass of carbon present and the mass of hydrogen present. From this, we can make use of the total mass of the sample and find the mass of oxygen present. So our statement is mass of oxygen present is going to be the total mass of sample, and the sample is already 2.0 grams. Total mass of sample, 2.00 grams, minus the combined masses of hydrogen and carbon present. Carbon present calculated earlier, 1.33, plus that of hydrogen present, 0.23 in grams. And upon evaluation, we have 1.23 plus 0.23 gives us 1.46, 1.56. And 2.0 minus 1.56 will give us, of course, we have 0.44 gram of oxygen. Now we have the elemental composition of the organic compound. 0.44 gram of oxygen, 1.33 gram of carbon, and 0.23 gram of hydrogen. Now the first stage of the calculation is complete. We have determined the elemental composition of the organic compound. 1.33 gram of carbon, 0.23 gram of hydrogen, and of course 0.44 gram of oxygen. Now, there is no point calculating the percentages of these individual elements because the process is the same for that calculation. For example, if we want to calculate the percentage composition of carbon, we're going to take the mass of carbon, 1.33, and divide by the total mass of the organic compound given to us, 2.00, and then multiply by 100. This process is the same for that of hydrogen and for oxygen, and therefore we can decide to skip this process and go to the next stage. So let's take the traces away for the next stage. Determination of the empirical formula is the next stage. Please come with me. For the determination of the empirical formula, let us use a tabular format. So let's form the table. And right there, we have the elements. Carbon, or hydrogen, and oxygen. Let's go straight for the mass present. And we have the masses of the individual atoms, or individual elements present. So for carbon, we have 1.33. For hydrogen, we have 0.23. As we obtained. And for hydrogen and for oxygen, finally, we have 0.44. Now, the next stage is to find the relative moles present. Relative moles of atoms. Relative moles of atoms. So we're going to divide each of these masses by the relative atomic mass and not the molar mass. So we have in the first calculation, we have 1.33 divided by relative atomic mass of carbon is 12. And this calculation gives us 0.11. The next one, 0.23, we're going to divide by that of hydrogen. So we have 0.23 divided by the relative atomic mass of hydrogen, not the molar mass, 1. Of course, that gives us 0.23. Finally, that of oxygen, 0.44. And we divide by the relative atomic mass of oxygen, which is 16. And this gives us 0.03. Each value to 2 decimal places. These are the relative moles of atoms. And finally, we get the simplest ratio of this by dividing by the smallest. So we have the simplest ratio. Simplest ratio of the simplest ratio of these relative moles of atoms. So we can, of course, have a demarcation here. That's right. So the simplest ratio will be dividing by the smallest of these values, and the smallest is 0.03. So we divide 0.11 to be divided by 0.03. And this gives us, of course, 3.67 to 2 decimal places, which we can approximate to the nearest whole number here, because 0.67 is very close to the nearest whole number there, which is 4. That's right. And now we divide the next one, 0.23, also divided by 0.03. 0.23 divided by 0.03. And this will give us, of course, 7.67, which is also very close to the nearest whole number 8. That's right. And finally, we have 0.03 divided by itself. Beautiful. And this will give us 1.00. And that is one whole number. And based on this ratio of combination of the atoms, we can have the empirical formula. And therefore, let us take it over here. The empirical formula can easily be written right now. The empirical formula of the compound can be written as carbon, 4 atoms of carbon, combined with 8 atoms of hydrogen with 1 atom of oxygen, which we do not need to write this one. And that is the empirical formula of the compound. Now, the final stage of the calculation of the molecular formula from the knowledge of the molar mass. The molar mass is given 144. And now we know the molecular formula is an integer multiple of the empirical formula. Based on that, we can launch straight into the last stage of the calculation. Let's get these traces away. And now we can state that let the molecular formula be an integer multiple of the empirical formula, which is C4H8O. And now multiply by N, an integer multiple of the empirical formula. And therefore, we can calculate the molar mass. To calculate this molar mass, N is multiplying every atom present. So we can have that N out there and then go on with the calculation. Carbon atom occurs 4 times. Relative atomic mass of carbon is 12. Now we have to multiply by 4 because carbon occurs 4 times there. Now plus the relative atomic mass of hydrogen is 1. And hydrogen occurs 8 times. Finally, the relative atomic mass of oxygen is 16. And oxygen occurs only once. Therefore, that bracket is not intended. So let's have it plus 16 for oxygen equals the molar mass provided, which is 144. And now let us evaluate this carefully. So we have N multiplied by the result. 12 multiplied by 4 is 48. Plus 1 multiplied by 8 is 8. And plus 16. All of this give us 144. 144 intended there. That's right. And now, if we add this together, 48 plus 8 gives us 56. Plus 16 gives us 72. So we have therefore 72N gives 144. And now this is an ordinary linear equation in one variable. We can isolate N by dividing both sides by 72. That's right, 72 divides through, leaving N. And now 72 divides into 144 gives us 2. Therefore, the value of N is 2. Now we can write the molecular formula. The molecular formula being C4H8O multiplied by N translates into C4H8, that's hydrogen intended there, H8O multiplied by N, and now we have the value of N to be 2. So N is 2 right there. We could take a moment to state it, of course. N is 2 right there. And that means the molecular formula, therefore the molecular formula can now be written. Molecular formula can be taken right now. You can already see it. C2 has to multiply all these numbers here. 2 multiplied by 4 gives us 8. 2 multiplied by 8 gives us 16. And of course, 2 multiplied by 1 there, 2. Beautiful and very simple. And clearly, our answer is right there in the option D, right there. This is very simple. Beautiful. Now, attached to this video are 2 quizzes that you can take and test your understanding of this video. So I encourage you to take the questions. Now, also provided as a link in the pinned comment is the test on chemical composition stoichiometry. I encourage you to take the test on chemical composition stoichiometry. There are 20 questions to be attempted in 30 minutes. This will help you to assess your mastery or understanding of chemical composition stoichiometry as a topic. And finally, if you wish to study fully the full analysis of the topic, chemical composition stoichiometry, there is another link provided that takes you to the full presentation of the topic, chemical composition stoichiometry. So I encourage you to study, learn, and enjoy. Thank you for being part of the session. And until I see you in the next video, you stay blessed.